All right, we are in now section 8.6, and we've learned about a lot about series. We've learned uh, tests that will tell us if a series converges or if a series diverges, and we've learned about different kinds of series. And in section 8.5, you learned about for instance, power series. So power series are series where the series involves a variable x. Ultimately, what we want to do is take a function and express that function as a power series. And in section 8.6, for a limited number of functions, you will be able to do that. So this section 8.6 relies on an important fact. Okay, it starts with an equation that you might have seen before. 1 divided by 1 minus x is equal to 1 plus x squared plus x cubed and so forth. So the function 1 over 1 minus x can be written as a power series. And in fact, this is a geometric power series with a common ratio x. And 1 divided by 1 minus x will equal its power series that you see in the gray highlighted box there for values of x between 1 and -1. So what I want to do first off is show you why this formula is true. I mean, the formula is so important, but you should know why. You should know why it is true. So on that note, let me show you why it's true. Okay. All right. So I'm going to bring up the notes now and go to a certain page. This is the page I want. Okay. And for our purposes here, we don't need analogously. Let's just say let's divide 1 by 1 minus x. So remember, let me just change the font here. The function that we're working with is 1 divided by 1 minus x. And we're trying to show that that rational function can be written as a power series. So, you know, anytime we divide, okay, we're going to take the number on top, okay, put that here, and then we divide by the bottom. This is how we do division, 1 divided by 1 minus x. Well, how many times does 1 minus x go into 1? It goes in 1 time, and 1 times 1 minus x is 1 minus x. Well, we're going to subtract that 1 minus x, and when we do that, nice things happen, because the 1s simplify out, and you're left with x. Then we have to ask, okay, 1 minus x, how many times does it go in x? Well, it goes in x times. X times 1 minus x is x minus x squared. We subtract x minus x squared, and that's going to give us a positive x squared. The x's cancel out. How many remember doing this kind of division in maybe pre-calculus or algebra? How many remember doing this kind of division? Okay, Ange remembers it. I've taught pre-calculus, and I know it's covered there. David remembers it. Okay, well, great. Well, we continue then. All right, well, how many times does 1 minus x go in x squared? It goes in x squared times. X squared times 1 minus x is x squared minus x cubed. If you subtract that, again, the x squared terms drop out, and you're going to be left with positive x cubed. And we can keep going with this. But look what we have up here. Look what's being generated. Okay, the quotient equals 1 plus x squared plus x cubed and so forth. And this is why we can say that 1 over 1 minus x equals this power series. And we recognize that power series as a geometric series that will converge when the common ratio is less than 1, or the absolute value of the common ratio is less than 1. Okay, so that's a formula, and that formula we're going to utilize a lot in like all the time in section 8.6. Okay. Now you'll learn later a more general way to express a function as a power series, but certainly this is an excellent concept here in section 8.6. Are there any questions? Okay, well, so let me go to the next page then, if we're good here. Okay, so here is the formula that we just derived. And what I'm going to do is modify the formula. Well, not really modify the formula, but I'm going to make a new formula. And instead of x, I'm going to put in, replace for x, an apple. Okay. I'm going to call this my apple formula. Okay. So if I follow the pattern of the formula above, formula 1, what would formula 2 be? Well, all I do is everywhere I see an x, I replace it with an apple. And so this is going to be my formula. And naturally, the absolute value of the apple has to be less than 1. Or we could say that the apple is between less than 1 and greater than negative 1. Let me give you a moment to copy that down. So the apple formula is not in the textbook, but they just sort of work the problems out, thinking that you'll think about this kind of this kind of apple formula. But I'm being a little more concrete. Are there any questions? Okay. Well, let's go to an example then. Let's get to an example here. Okay. So here, well, let me let you copy the example down. And incidentally, while you're copying, I forgot, how many of you is that helpful to have those, you know, the remediations giving you till December 12th I guess it would be 2:30 p.m., right? Because you have to finish the way, you know how examining works. All right, Taj is liking that. Wonderful, wonderful. All right, good, good. All right, so here is an interesting rational function. Well, I hear you, David. I hear you. The option's there, and you certainly don't want to wait till the last minute to do your remediations. Uh, but I hear you. I hear you. You know, if you can help it, right? All right. So here's your function. F of x equals 1 divided by 1 plus x squared. And we want to express that function as a power series. Now, we know we already talked in section 8.5 about an interval of convergence. So when you have an interval of convergence for a power series, that's the interval of x values over which the power series converges. So if we're going to come up with the power series for this function, then we certainly need to know the interval of convergence for that power series. Okay, because the function. Well, you'll see this. So okay, so what we know, of course, what do we know already? Well, we have a formula for 1 over 1 minus x. 1 divided by 1 minus x is equal to the power series from n equals 0 to infinity of x to the nth power. And that is true when the absolute value of x is less than 1, or x is between 1 and negative 1. Okay? So, all right. So, but this function here doesn't look quite like 1 over 1 minus x. Okay? But yet, yeah, and I want to be more clear. We can do a little more. We have 1 over 1 minus an apple, right? We have a formula for that. Okay, that'll equal the summation where n equals 0 to infinity of the apple to the nth power. And this is true when the absolute value of the apple is less than 1. So that's fine. That's fine. But how are we going to manipulate this function to make it look like, you know, like this function here? I mean, for instance, we have a minus there. We do have a 1, okay, and a 1 here, but we have a minus, whereas here in the function we have a plus. So let me show you how we would do this. One moment. Okay, so let me just go forward here a little bit. Here we go. So our function is 1 over 1 plus x squared. And let me write down that apple formula again. Whoops, hold on. Keep messing up here. Yeah, 1 divided by 1 minus an apple equals this power series. And that's true when the absolute value of the apple is less than 1. So that's fine. That's fine. So what we can do is we can write plus x as 1 minus negative x squared. And the negative x squared would be my apple. Then, okay, I use the formula here. So, and I come up with this power series here. And incidentally, the absolute value of my apple has to be less than 1. Well, the apple is negative x squared, right? So I have the absolute value of negative x squared is less than 1. Well, that just means the absolute value of x squared is less than 1 because the negative goes away. And the absolute value of x squared is just x squared. So if x squared is less than 1, that means that x would be between 1 and negative 1. Because, like, for instance, if you draw a graph of, y equals x squared, okay, and here's 1 and here's negative 1 on the x-axis. Okay, I'm sorry, it's not the prettiest picture, but those values at x equals negative 1 and 1, the function equals 1, right? So it's the function will be the x squared, y equals x squared, and that's right. That's what I have written here. But let me make it a little neater. Y equals x squared. Okay, so it's between 1 and negative 1 that function is less than 1. So that's how we arrive at this for my interval of convergence. And incidentally, because the apple formula is based on a geometric series, it's a geometric power series, we know that when the absolute value of the apple is greater than or equal to 1, the power series would diverge. So we don't have to, unlike the power series that we saw in section 8.5, the power series in section 8.6, we do not have to test the endpoints of our interval for convergence. The intervals of convergence for the section 8.6 problems I want to be careful about how I state it, but in general, for the problems you're seeing, the intervals of convergence in section 8.6 will be open intervals. Okay, you do not have to test convergence at the endpoints. So, okay, we're down to here. This is good. And the thing is, this power series, we're going to want to write this power series here in a nicer format. So the negative x squared, I'm going to write that as negative 1 times x squared. I'm raising that to the nth power. Well, that will give me a series where my term inside is negative 1 to the nth power times x squared to the nth power. Well, x squared raised to the nth power gives me x to the 2nth power. And so now the series is in a very nice format. Okay, very nice format. And I decided just to write down some terms of the power series for you. So, like, the 1, how do we get the 1? That's negative 1 to the 0th power times x to the 2 times 0th power, the negative, so that's the first term. Hold on. That's the first term. The second term, which is negative x squared, that comes from taking, okay, well, negative 1, n started at 0, next one is n equals 1. So negative 1 to the first power times x to the 2 times first power, that's x squared. I mean, I think you can see how I'm getting all these terms here. The plus x to the 4th, okay, that comes from taking negative 1 to the 2nd power times x to the power 2 times 2, and so, yeah, does it help to write how many find it helpful to list out some of the terms of the series? Is that a helpful thing for you, just to kind of give you just a little bit of an intuitive feel of the terms of the series? Okay, Ange likes that. Tosh likes that. Wonderful, wonderful. All right, so we've identified a power series representation for our function. Are there any questions before I move to the next page? Okay, so we've established that this rational function, and rational functions are sometimes hard to work with, you know. Um, you probably learned that in pre-calculus. They can get a little bit complicated, but the nice thing is using the Apple formula from section 8.6, I can take a rational function like 1 over 1 plus x squared and write it as a power series. Now remember that it's only good over the interval of convergence. Okay, so let me just make a note here. So let's say you have 1 divided by 1 plus let's see here, 0 squared. Is that equal to 1 minus 0 squared plus 0 to the 4th minus 0 to the 6th plus 0 to the 8th minus so forth? Is that true or false? Okay, Taj. And Taj, why is it true? Why is this statement true? What can you tell me about x equals 0? In regards to the interval of convergence? What can you tell me about x equals 0? Well, the series on the right does equal 1, but that's right, Taj. 0 is less than 1 and greater than -1, right? It falls in the interval of convergence. So that's absolutely cool. Let's look at something else. Let's say you had 1 over 1 plus 2 squared. Now we know 1 over 1 plus 2 squared equals a fifth, right? But if we use the power series, we'd have 1 minus 2 squared plus 2 to the 4th minus 2 cubed. I'm sorry, I'm not doing this right. Hold on. Okay, so 1 minus 2 squared plus 2 to the 4th minus 2 to the, 6th plus 2 to the 8th minus dot, dot, dot. Is this true or false? This statement here. What do you think? Do you think that 1 minus 2 squared plus 2 to the 4th minus 2 to the 6th power plus 2 to the 8th power, do you think that's going to equal 1/5? Ah, all right. So this is a false. This is false. Now, why didn't that work out? That's false. That's false. That's not true. Why is it not true? Why is it the power? Why can't we take the function at x equals 2 and use the power series? That's right. Good, Inch. Good, Mario. 2 is not in our interval of convergence. It's not in there. So we cannot use power series representation for a function to evaluate the function at x equals 2. I look at intervals of convergence as kind of like a guarantee, like a car. Like if you think about when you buy a car, uh, I mean, anytime you buy a used car, try to get a warranty, right? But you go to the used car dealer, like I don't know. I haven't bought a used car honestly in a long time, but like trying to think of like that CarMax. CarMax. Does CarMax have like warranties on their used cars? I don't know, but does anybody know offhand? Um, okay, Mario says yes to that. So that tells you what the car is good for, right? How long? So I look at interval of convergence for a function as something similar. It tells you where the power series for that function applies, for what x value it applies. And you can't use the power series to evaluate the function outside for values of x outside the interval of convergence. Okay, great. Let's do another example here. Let's proceed on. Okay, let's look at another function. Let me give you a moment to copy down this rational function. Okay, so all right, an interesting rational function, and this function x cubed divided by x plus 2, we want the interval of convergence. And incidentally, once you identify the interval of convergence, it's no problem to figure out the radius of convergence, right? Because the radius of convergence is half the length of your interval of convergence. So, okay, let's proceed to the solution. So again, let's remember what formula we have in our hands here. The formula that we know is 1 over 1 minus an apple is equal to the power series and equals 0 to infinity of apple to the nth power. And of course, that applies when the absolute value of your apple is less than 1. Okay, because that's a geometric series and the apple is your common ratio. So, okay, what I do is I say, okay, I gotta try to make my function resemble my apple formula. So the x cubed on top, I'd like a 1 on top. So I'm gonna factor out an x cubed from the numerator, and I can worry about x cubed later. Let me focus on 1 over x plus 2. Now the x plus 2 in the denominator, I can write that as 2 plus x. I can do that. And I recognize that in the apple formula, I don't have a 2 down there in the denominator. I have a 1. So I can, though, get a 1 by factoring out a 2 from both terms. So the 2 plus x, okay, in the denominator here, I can write that as 2 times 1 plus x over 2. So, okay, well, now I got a 1. Now I got a 1. So I'm happier. Got a 1 there. And this 1/2, I can, move it out in front of, that fraction. So the only thing left is I want a minus. I want a minus, right? Because the Apple formula, so hold the thought there. My Apple formula has a minus there. So, okay. 1 plus x over 2 can be expressed as 1 minus negative x over 2. And now this fraction here is in the right form to be able to use the Apple formula. It's in the right form. So, okay, we can apply the Apple formula and get a power series. And we recognize that the common ratio is negative x over 2. So remember, geometric series can have negative ratios also. But where is the power series defined for this function? It's defined for when the absolute value of the common ratio is less than 1. So we have here the absolute value of negative x over 2 is less than 1. Well, that's the same as saying the absolute value of x over 2 is less than 1, because the negative goes away. And I can write the absolute value of x over 2 as just absolute value of x over 2. And of course, we can multiply both sides of that inequality by 2. And then the 2's will simplify out, giving us then that the absolute value of x is less than 2, or equivalently, x is between negative 2 and 2. That's your interval of convergence. So anytime I do a replacement of a I replace this function here, 1 divided by 1 minus negative x over 2. When I do the replacement and put in the power series, I right away identify the interval of convergence. Okay. And since the interval of convergence has length 4, the radius of convergence, r, would be equal to 2. So in your homework for section 8.6, they're always asking about the radius of convergence. Are there any questions about this so far? Are we okay so far? Who's feeling somewhat comfortable? Or I should say comfortable, but who's feeling, okay, Ange is reasonably comfortable, and Taj is, and Mario, excellent. Are there any questions? All right, well, our job's not done yet. Our job's not done yet, okay, because let me just clear the annotations here. So we know we have our function, okay, our function equals this expression here, but I want to get it in simplified form. So let's, and there's going to be value in getting it in simplified form. So let's do that. Let's go to the next page. Okay, and here was our result. And negative x, we have a negative x here, right? That equals -1 times x over 2, and that quantity to the nth power. And so you see, I can just break down the expressions in the power series. So that the power series looks nicer, simplified. Now we have that x cubed over 2 in front of the summation. Is it okay to bring the x cubed over 2 inside the summation? It appears to be okay. Why is that? Well, does x cubed over 2 depend on the index n in the series? Is x cubed over 2, does that depend on the index n? It does not. That's right, Ann. So we can bring it in. I mean, put it this way: from your knowledge of power series, you'd have no problem taking x cubed over 2 and factoring it out in front of the summation. So therefore, why can't you go the other way? And we want to do that because, again, this will allow us to simplify things. So you know, this expression here in the summation sign, we could express that as -1 to the nth power, okay, times x cubed times x to the nth over 2 to the first power times 2 to the nth. And so, you know, we add exponents and then we get this result here. And then I wrote out some terms of the power series. I thought I'd write out some terms. So like the first term here, when it is 0, you know, we have -1 to the 0th power over x to the 0 plus 3 power all over 2 to the 0 plus 1 power. And that gets us a half x cubed. If we have the second term, -1/4 x to the 4th, okay, how do we get that? Well, that's when n is 1. Okay, so we have -1 to the first power times x to the 1 plus 3rd power all over 2 to the 1 plus 1 power. Okay, 2 to the 1 plus 1 power. One moment. All right. Sorry, class. One moment. Okay, thanks. All right. So you see, you can just keep showing that why the terms are they are. So there you go. There you go. So you have now your power series. So in WebAssign, the answer that likely would be, if it's like a multiple choice problem, would be the power series in this form here. Are there any questions? All right, I'd like to do one more before we take our break. Let me do one more with you. Let me go to the next page here. This is really quite lovely math that you're seeing. Let's take a look at this problem here. I'll give you a moment to copy that problem down. All right, class. So this is certainly an interesting function. And what makes this a little maybe harder to deal with, or I'll say more interesting to deal with, is you have that second power in the denominator. Okay, so we're going to have to do some differentiation to help us with this problem. Okay, let me show you here. Let's just go right to the solution. Okay, so first what I do is, well, let me write down the original function here. The original function was equal to x divided by 1 plus 4x squared. Okay. So I know that 1 plus 4x down here is going to be something that I'm going to have to deal with. So I'm going to just look at the function 1 divided by 1 plus 4x. And I'm going to rewrite that as a power series. So 1 plus 4x I write as 1 minus negative 4x. And then using the Apple formula, that'll be the series where you have negative 4x to the nth power. Okay. Now I'll mention this. Negative 4x to the nth power is negative 1 times 4 times x to the nth power. So that equals negative 1 to the nth power times 4 to the nth power times x to the nth power. And that's how we get what you see here. And the interval of convergence is from negative fourth to a fourth. Okay. So without getting too technical, our interval of convergence for this problem should be negative fourth to a fourth. Now, how am I going to relate this power series that has been derived to this function here? Well, what we can do is we can differentiate the 1 over 1 plus 4x. Now, instead of using the quotient rule, I'm going to write 1 over 1 plus 4x as 1 plus the quantity 1 plus 4x to the negative first power. Okay, and that's what I do there, because I always prefer to use the power rule as opposed to the quotient rule, although sometimes we need to use the quotient rule. And naturally, we're using the chain rule here to get the derivative. And now that I have the derivative, I'm going to write that as negative 4 over 1 plus over the quantity 1 plus 4x squared. So we've established that the derivative, hold on here. We've established that, let me see here. Sorry. Let me just write something in here. So we've established that the derivative of 1 divided by 1 plus 4x is equal to negative 4 over 1 plus 4x quantity squared. But that's the same then as saying that the derivative of the power series for the function 1 divided by 1 plus 4x, the derivative of this power series okay, equals -4 over 1 plus 4x squared. So that then brings us down to this this statement here, which I just rewrote. And it's interesting. You have the derivative of a summation here, right? You have the derivative of a sum. But you've learned that if you have the derivative of a sum, that equals the sum of the derivatives, right? And if you have the derivative of the sum of 3 functions, that just equals the sum of the derivatives of the 3 functions. Well, what do I have? What do I have here? What do I have here? I have the derivative of an infinite series, which is the sum of an infinite number of terms. Well, that's just going to be the sum of the derivatives of each of the terms. See that? The derivative of a sum is the sum of the derivatives. Are there any questions on that? All right, well, now we're differentiating, right? We're differentiating with respect to the variable x. And x to the nth power is the only variable function. It's the only part of the function with an x in it. We can treat -1 to the nth power and 4 to the nth power as constants, right? Because we're differentiating with respect to x. So what I do is let me actually show this step on the whiteboard. I'll pop back here. Hold on. Let me just show this step on the whiteboard. Whoops, hold on. Where'd my whiteboard go? Hold on. Let me clear that. Okay. So one moment here. Okay, so here's our summation. And what we can do, see, is we can bring the -1 to the nth power and the 4 to the nth power out in front of the derivative, because we're differentiating with respect to x, and those two terms aren't dependent on x at all. See that? Okay, and so then what we have the derivative of x to the nth power is n times x to the nth power minus 1. Now, I'll mention this while I'm here. Are there any questions on that? Is it pretty straightforward? It's really beautiful math, that's for sure. What I'm going to do is I'm going to write out the first term of the series plus then the rest of the series, which starts at n equals 1. I mean, I can write my power series this way. I can do that. And what is this first term equal to, where we had n equals 0? Oh, wait, hold on. I got to put a 0 here, don't I? Forgot about that. Okay. What's that first term equal to? Zero. That's right, Mario. Because you have a 0 here, right? So this means then that this power series, though it starts at n equals 0, we could start it instead at n equals 1, because the first term is 0 of the power series. Okay, so I wanted to make you aware of that, because let me go back to the solution here, if we're good on that. Let me see here, where was it? Yeah. So I don't need this little black line here. Really is just pretend it isn't there. Well, Sansar, for this particular problem, we needed to take the derivative of our power series. Well, we're not done yet. We're not done yet, but we've established there's for maybe 1 or 2 problems in your homework, you might need to take the derivative of the power series like we did here to get the result that we need to get. We're down to here, okay? We're down to here. But then they go back, you see, they go back to putting n equals 0 in there. What's that about? Well, let me show you. So, I mean, we're going to walk away like the final, I want to say it's the right way. Hold on. In this problem, they're saying that this power series here is equal to this power series. And I want to show you that. So let me go to the whiteboard. Clear this out. So sorry about the background noise here. All right, so few of us live alone, right? So here we go. All right, this is the power series that we're at. But what they do is, in this problem, they say, okay, well, let's start the power series at n equals 0. Let's go back to n equals 0. But if we do that, then we have to make an adjustment on the powers. So anywhere I see an n here, I'm going to replace the n with an n plus 1. See that? I replace all the n's. Gosh, come on, give me red. Give me red. All n's with n plus 1. And the reason I have to do that is if I adjust the power series so it starts at n equals 0, then the nth powers, see here the nth powers start at n equals 1. Well, if I start at n equals 0, I have to adjust my powers by adding 1 so that the first term of the series, so that the terms of the series are the same. Okay, that's what you have to do. And see, WebAssign, what will happen is they sometimes, like, you'll have a multiple choice problem. You'll have the multiple, like a problem, and the answers are all multiple choice. And you have to find the right form. You know, you have to find the right form. So the right answer. And you don't want to force an answer. If you get a power series and it doesn't match one of the power series there, you have to sometimes make these kind of adjustments. Okay, and so that's why I'm showing you this. So we have now, we have that -4 over 1 plus 4x squared. We've established that that equals this power series. But remember, the power series, that the function that we want our power series for is equal to x divided by 1 plus 4x squared. Okay, that's what we want our power series for. Well, this function here is pretty close. It's just we have to make an adjustment on it. So let me show you that adjustment. Let me go back to the solution here, because I want to, you know, finish this problem up. Oh, good, Sansar. Excellent, excellent. And I'm sorry, I didn't know you had a question, Sansar, but I'm glad I answered it. I'm happy about that. So, you know, here's where we're leaving off. Let's now finish this problem off. So what I'm going to do is I'm going to take this function and the x divided by 1 plus 4x quantity squared, and I'm gonna write that as -4 divided by the quantity 1 plus 4x squared times -x over 4. And that's going to be great because I have the power series. Right, for -4 over 1 plus 4x squared. That's this power series. And now the -x over 4, I can bring that inside the power series. And then I can just simplify things and get an answer. Get the final answer for this power, so you know, x divided by 1 plus 4x quantity squared equals this power series. And of course, let's keep in mind that the interval of convergence should be from -1/4 to 1/4. So the function doesn't equal the power series for all values of x, but it'll equal the power series for the value of x, the values of x that fall between -4th and a 4th. Okay, so this is an example where we had to differentiate a power series to help us get the answer. So you might have 1 or 2 questions on your section 8.6 homework like that. Are there any questions at all? Right? Who's reasonably comfortable? I mean, I know you have to practice to get fully comfortable, but who's reasonably comfortable, at least partly comfortable? All right. All right, Taj. All right. You know, it's going to take a little time to get comfortable, but comfortable for you to get comfortable with it. All right, Ange, very good. This is some of the most beautiful math that that probably you have seen so far in your math careers. Working with the power series, and it's just amazing. And there's more to come. So, all right, let me stop the recording.